All right, guys, so this lesson we're gonna be talking about rotational kinetic energy, okay? So, all right, first thing is, what is rotational kinetic energy? So we're gonna define, well, let's have a look, what is linear kinetic energy? Because all linear quantity can go to become rotational quantity, okay? So linear kinetic quantity, they say Lin, so that's linear, so that equals half mv squared. Sometimes we also call this transitional kinetic energy because linear going forward, it just means transitional. It's the same thing, kind of going forward, backwards, okay? All right, so, and now we're gonna convert that into rotational kinetic energy, ROT, rot, EK rot. If something is rotating, you also have kinetic energy for that rotation. All right, so that equals half, instead of have m, now we have I. Well, and then instead of have speed, now we have angular speed omega. That becomes half I omega squared, okay? So previously, when you guys do a conservation of energy question, say this. If you got this thing coming down, right? So if you got an object coming down, rotating to the bottom, so what you did was you say, well, gravitational potential energy is gonna equal to kinetic energy, right? And then you say, well, then that is mgh equals to half mv squared. So that's what you did previously, okay? From level 2, that's all you need to do. But this year, now, not only this thing is half mv squared going forward have a kinetic energy, the thing itself is actually also rotating. If something is rotating, you have a rotational kinetic energy. So this energy, not only does it turn into this one, actually it also turns into rotational energy as well. So this year we say EP still equals to EK, but it actually equals to EK linear, which N plus EK rotational. Okay, and then what we got is gonna be mgh is gonna equal to half mv squared and plus half I omega squared. So this is going to be the new equation that we're going to be using this year to calculate this type of question, okay? And some other type of question are this. Well, yes, you can have gravitational potential energy sliding down. You can also have something sliding up. So then you will have linear energy and rotational kinetic energy. These two act together, turn backwards into gravitational potential energy, make it going up. Okay, all right, so another example of this is this. If I have this pen, right, so I'm gonna throw it upwards. If I throw it upwards and then I'm also gonna rotate it, if it's just spinning in air, so what is the energy that's gonna turn into gravitational potential energy? In this circumstances, if I'm just throwing it upwards, the pen, even when it's reaching the highest position, it's still gonna be rotating. So then this rotational kinetic energy is not gonna turn into gravitational potential energy, okay? But the upwards, the translational or the linear speed is going to be turning into gravitational potential energy and then falling down. If this is the circumstances, then you're going to apply last year's method, which is just this, okay? You don't ignore the rotational, but if it's moving along the ground and that's rotating, and then you will need to use this new method over here. So using this part, okay? All right. So now we can use this to calculate some questions, and I'll give you guys a calculation question now. So let's have a look how it works, okay? Let's look at an example. So the example I'm gonna have is some numbers that I got from the textbook. This textbook, question 1, I'm using the same question, numbers, but I'm just going to ask you one question. Say this. Well, the ball, this thing is going to be a hollow ring, and so the mass is contributed on the outside over here, and I'm going to give you the mass is 0.7 kg, and this thing has a radius which is 0.27 meter, okay? And then you're going to have a height which is 1.2 meter tall. So now this ball is going to start to roll down, okay? And the question is, they're going to ask you, well, what is going to be the ball's rotational speed at the bottom? oh, I say angular. And then we'll also ask the linear speed. Okay, and let's have a look. First, before we do this question, let's have a look of a rolling situation. Say this, if I have something rolling on the ground like this, say this ball is rolling on the ground, right? So if it has a speed going over here at v going forward, and then all of the points over here is going to have a rotational speed at v as well. The reason for that is because this distance, if you move the distance from here, say to here, like that's the distance, and then you're going to move forward a distance as well. Say if that's d, and that's going to be your d. The move forward distance is going to equal the distance going forward, and that takes same amount of time. And because v equals distance divided by t, so if this thing, say I'm going to use this as an example, if this thing moves forward 1 meter, if it moves forward 1 meter, and then this part, any point on the outside is going to be rotating 1 meter, so then it can go forward. So that's why the rotational speed on any point on here will equal to the amount of speed is going forward. Okay, so now let's come back to here. Let's see how we can solve the question. Okay, so we're going to be using conservation of energy, so which is EP is going to turn into EK. Okay, EP is turning into EK rot plus EK linear. Okay. And then what we're going to do next is we're going to use MGH equals half NV squared plus half I omega squared. Okay? All right. So once I get this, I'm going to keep going. I mean, I can put the numbers in there to calculate, but I think I'm just going to keep going and rearrange the equation, okay? If we found it's easier to put number in there, then put number in there. That might make it easier, okay? All right, so that's going to equal to MGH equals to half MV squared plus, well, because we got V, we got omega, both of these numbers, like, we are unknown. So we'll probably need to, like, just make it into, like, one number. And then, so we can calculate, say, we only have one x. We don't have xy in one equation, right? We only have x in the equation. We can solve the x. So that's why we have to make these somehow the same. But let's have a look, how do we make them the same? Okay, 1i. Well, what is I? I equals, this is a hollow ring, right? Hollow ring, if it's mass on the outside, that equals to mr squared. That is going to be your I. So I'll write over here, what are the equations we've used? I equals to mr squared. Okay, so that is one equation we've used here. Okay, and then we're going to use omega, and as we've learned, omega equals V divided by R. So the equation we're using is V equals to omega R. So omega equals to V divided by R. So this is the equation we're using over here. So just having a look, see if you can see it pretty clearly. Okay, see it? Okay. Okay, so now let's have a look. Well, now I can rearrange to calculate V somehow, right? One other method you can do is you can put V equals omega R over here. You can get calculate omega as well. That's fine as well. Okay, so let's have a look at this situation. All right. In fact, if you can see here, how big is the mass of the object doesn't matter, because you got a mass here, mass here, mass here. So it's the same kind of situation where it's like if you have an object like dropping, it does not matter how much mass the object has, they actually always fall down at the same speed. So this situation, as long as the shape, the radius, if the radius don't change, the height don't change, and then the speed will not change. Okay. Okay, so we're gonna continue to do that. Let's just pretend that we can Well, we're not pretending. We're actually we can delete the mass, but you can put the mass in there to calculate. Okay, I'll make it easier. I'm going to delete the mass over here. I'm going to delete this mass over here as well. Okay, all right, and then I'm going to keep continuing calculating. Say, well, the height is 1.2. To make the calculation easier here, I just put 10 in there, but in your actual exam, obviously you have to use 9.81, right? So, and okay, I'll just time 9.81. Yeah, let's just make it like good, you know? Okay, so that's gonna equal half v squared and plus a half over here. Well, happen to be perfect. This r squared, so r squared, then this is v squared over r squared. Well, this v squared can actually cancel each other as well. So then we just got, well, 1.2 multiplied 9.81 equals to half v squared, add half v squared, become v squared. Wow, how easy is that? Now, v is just going to equal to 1.2 times 9.81. That will give me the answer. Okay, so let me put that in my calculator. So 1.2 times 9.81, that equal to this, square root, so it becomes square root 1.772. Okay, and then I'm gonna go, okay, square root 1.772, that will give me 3.43 meter per second. All right, so that is the answer. So 3.43 meter per second. And then I want to find the angular speed, and then obviously I can just use the v equals omega r, and then omega equals v divided by r. So that equals 3.43 divided by radius, which is 0.27. So that will give me 12.7 rad per second. Okay, and that's it. And that is one typical question over here about this situation, how the rotational quantity and is playing a factor. The kinetic energy is going to need to be considered in this situation. Okay, and obviously each question are different. So you're going to analyze the question and yeah, and then decide which way you should use. Okay, sometimes they might say, oh yeah, so sometimes EP is the same, equal to these two. Both of them turn into this. Sometimes only EK is going to be turning into EP, or EP turning into EK if it's throwing upwards or downward. So you're going to look at the situation. So if it's rolling, and then this is the way to do it. Okay. So cool. All right. And then that's it for this video. And I'm going to make another video about comparing hollow ring like this situation to a solid disk, and that is in the notes as well, and how does that work. So we'll have a look at that next video.